So hello, I want to look today into epipolar geometry and give you an idea what epipolar geometry is. It's something that we use to, if we work with image pairs, in how to give us some information how about a point from image number 1, for example, is mapped into the image of image number 2, and this simplifies us the search for corresponding points, for example. So again, a camera pair, maybe a stereo camera as the one shown over here, but this is just kind of one possible examples. There are other ways of camera pairs for which that actually applies. And so what we typically have is we have one camera sitting in the projection center here, a second camera sitting in the projection center over there, and the two rays intersect at one point. This was a coplanarity constraint that we have been exploiting in the when computing the essential matrix as well as the fundamental matrix. And this also will play a role in here. And what we typically are faced with in reality, that we have an image pair, so two images, and we look into image number 1, and maybe we find a feature point and say, oh, this is a promising feature point. Let's see if I find this point in image number 2. And then I need to search for this point in image number 2. And where should I search for this point? Do I need to search the whole image, or can I reduce the search to in the second image? And it turns out that epipolar geometry is actually helping us with this. So given a point seen in the first image, and we have pixel coordinates of this point only, we want to find where is this point in my second image. And for this, I can exploit the so-called epipolar geometry, which takes into account the stereo pair, the baseline vectors, where points are mapped to, and that the direction rays also lie within planes, and how those planes from the 3D world are actually mapped into the image. So the epipolar geometry is typically used to describe the geometric relations in image pairs. And one of the key things is, as I said, it enables an efficient search when I look for corresponding points. And it actually turns out, if I have a point in image number 1 and want to look for a corresponding point in image number 2, I can reduce the search from a 2D search space, searching the whole image, to actually a 1D search. So I just need to search on one specific line. So it reduces the search space from 2D to 1D. This has several advantages. The first one, of course, it's faster, that's obvious. But the second one is also it reduces the possibilities for making data association mistakes. Because you may have multiple objects in an image which are self-similar or similar to each other. And if you then have one corresponding point, or one point in one image, you want to look for a corresponding point in the other image, you may have multiple objects which look identical, so they would generate very similar feature descriptors. But through the restriction of the search from the whole image onto a line, so-called epipolar line, as we will learn later on, will allow us to reduce the search space, and therefore may result in the fact that only one object of the self-similar ones is actually intersected by this epipolar line, and has definitely the chance for reducing the possible mistakes that we can do when making data associations. So this is a figure over here that will actually pop up pretty often in the course here. So we have our image number 1 over here, our image number 2 over here. These are the projection centers, O prime and O double prime, and this is my point xi, which is my real world point in the real world. So this point x is mapped over here in my image number 1, and this is projected to this point here in my image number 2. And I may have a second point y over here, which is mapped to a different location, and a different location over there. And what I now want to do is I want to go through the individual elements of this epipolar geometry drawing here, and then we can derive certain properties that those points will actually have to discuss then. So the first thing which is important is the epipolar axis. The epipolar axis is the line connecting the two projection centers. So it was like the baseline that we had before. It's something we call the epipolar axis. And then we have a plane which is spanned by O prime, O double prime, and let's say our point X that we are considering here as a point we are seeing in both images. And this is actually a plane, the so-called epipolar plane. So if I have a corresponding point, this corresponding point will actually generate an epipolar plane, but different points in the 3D world will lead to potentially different epipolar planes that we may have. And then we have certain points which are the so-called epipoles, an epipole in every image. And the epipole is the projection of the other camera's projection center into the image. So I'm here projecting the projection center of camera number 2 into the image of camera number 1 and the other way around. So this gives me my so-called epipoles E. And then we have something which is called an epipolar line. And this epipolar line is the projection of the epipolar, or the intersection of the epipolar plane with the image plane of an image. So let's say I have the epipolar plane which has been generated for this point X over here, for this point in the real world. Then if I intersect this plane with the image plane 1, I get this epipolar line over here. And the same over here. I get this epipolar line over here, which is intersection. Okay, so it continues like this. It's the intersection of the epipolar plane with this image plane over here. And this is an important element because, as we'll see later on, this will be important for finding these potential correspondences. And we can see actually why is this the case. So let's say I have this point X over here, and I want to find other corresponding points in my image number 2. So if I just have this image here, I have basically a direction vector to this point X over here. What I do not know is where is this point actually on that line. I just know it's somewhere on that line, from here to here, somewhere over here. So if I take this point now U and slide this point U on this line and project this point U into the other image, this point will actually slide along this epipolar line. Because if I'm moving X closer here, this epipolar line will move closer to the epipole. If this point goes further and further away, this line goes further in this direction. And so wherever this point X is, I know it's on this line, this line here will be projected to this line over here in the image, which is exactly the intersection of the epipolar plane with this image plane. So I can reduce the correspondency of the search to this epipolar line. And this is what it in the end will actually boil down to. Okay, so the epipolar axis, just kind of defining the important elements that we discussed a bit further, is the given through the basis, which is the connection of the two projection centers. So that's pretty easy and pretty straightforward. The epipolar plane is a plane defined by 3 points. By the two projection centers, that's always the case, and then by the point in the 3D world, which is defining this epipolar plane. So it's actually very similar to the coplanarity constraint that we discussed for deriving the fundamental matrix before. And so why is this thing called the epipolar axis? If I choose a different point in the 3D world, then those 2 points, O prime and O double prime, are always part of the epipolar plane, but this point X not anymore. So if I take Y, I still have the plane which connects these 2 points, but a different point in the 3D world. So I can generate this plane by basically rotating a plane around this axis. So I have my 2 cameras, the connection like this line between the 2 cameras, and then the epipolar plane I'm rotating around the axis are all the planes in the 3D world which have this vector here in common. So every point that I have, basically now if this is exactly horizontal line, it depends basically just on the height of that point, which will define the epipolar plane, and I can express all the epipolar planes by a plane rotating around the axis. And therefore, the thing is called the epipolar axis. And so I had the epipoles, which were the projection centers of the projection center of camera number 2 projected in the image of camera number 1 gives me the first epipole, and the other way around. So the projection center of camera number 1 projected into image number 2 gives me the other epipole. And then I have these epipolar lines, which are basically the projections of the rays which pass from camera number 1 to the corresponding point, projecting this line into the camera image of camera number 2. And of course the other way around. This gives me the two epipolar lines. So I can also write things as the epipoles is the intersection of the basis with the image plane number 1 and the epipole is the line, the epipolar axis, which is intersected with the image plane of image number 1, and this E is the image plane of image number 2. So this is basically the intersection of the line with the corresponding plane. And also the epipolar lines, as I said before, I can express through intersection of the epipolar plane with the image plane of image number 1 or the image plane of image number 2. And that's basically the element that we have here. So this was our epipolar plane, this was the image plane 1, image plane 2, and the corresponding epipolar lines. And the epipolar line is the thing we're typically looking for if we look for correspondences. So this is kind of the key element in here. And also the epipole is an important point because this is just the intersection point of all epipolar lines within an image. So in the epipolar plane, under the assumption that we have a distortion-free lens, are the two projection centers, the point that I'm considering at the corresponding point, because the epipolar plane depends on that point, the epipolar lines, because it's the intersection of the epipolar plane with the image plane, the epipoles itself, because the projection centers lie in the plane, and this is the intersection of those points with the image planes, and the image points itself, so where the points are connected. And these are all the elements that look in the epipolar plane. So you can see the epipolar plane is a constraining element that we can exploit when we look or search for certain things. And this is especially important for the task of predicting the location of a corresponding point in another image. And that's the point where this is important for us, because it allows us to restrict the search space if I look for a point in the other image. So in the end, this reduces me the search space from a 2D search space to 1D search space. So if my task is to predict the location of point, where the point X is projected into image number 2, assuming I know where it is in image number 1, I know that it must be the epipolar line, the epipolar plane is defined through that point, given this point X prime, so what I know from the first image. So the intersection of this epipolar plane with the image plane of image number 2, where I'm looking for the correspondences, will lead me the epipolar line in image number 2. So I just need to search along this epipolar line in image number 2 in order to find the potential point. So I'm reducing from searching the whole image to searching along a line. So in the next part, I want to look into computing the key elements of this epipolar geometry. And these are important quantities that we have described now, but we haven't really seen how we can actually compute them. So how can we actually sit down and write down the individual elements? And we want to look how we can actually compute them based on the projection matrix, P, or based on the fundamental matrix. So the properties that we know from our camera, how can we describe the different elements of the epipolar geometry? So the first thing is the epipolar axis B. And again, the epipolar axis can be directly obtained if I know my projection vectors, and here is explicitly expressed an homogeneous vector expressing that we only know the direction, but we do not know the length of this axis. And so once we have the projection centers, and we know we can obtain the projection centers based on our projection matrix, then we can also compute directly the epipolar plane, epipolar axis, sorry, the epipolar axis. So the next thing we do is we want to compute the epipolar lines, because these are things that we are typically interested in. And so if you remember, we are now here in the image plane, and if you looked into homogeneous coordinates, you may remember that the simple test if a point lies on a line in the 2D world is simply by computing the product of the two vectors with each other. So x is our point transposed times the line must be equal to 0. This is exactly the case when the point lies on a line. So we actually get this expression x prime transposed L must be equal to 0. So this is the constraint that this line must fulfill if it is the epipolar line for the point that I'm observing actually in image number 1. And now we can exploit the coplanarity constraint that exists, that we actually exploited for computing the fundamental matrix, that this point, the vector x that is defined through this x1 and the vector which comes from the other camera must actually form the plane, which is our epipolar plane. So, and just by comparing this to the coplanarity constraint that we derived through the fundamental matrix, we can actually see that in this equation, this is the same part, this is the same part, so this part should actually also be the same. So it means the line, the epipolar line described in that image, in image number 1, is nothing else than the fundamental matrix multiplied with the point generated in image number 2. So this is the epipolar line in this image number 1. So just by comparing those two expressions, I can actually see how the line equation must look like. And I can compute the line in homogeneous coordinates just by multiplying the fundamental matrix with the point stemming from the other image. That means the epipolar line can very easily be obtained by just using the fundamental matrix and the image, the point in the other image. And here the important thing is, so this is a fundamental, the epipolar line in image number 1. And the only thing I'm exploiting is the fundamental matrix and the point in image number 2. So knowing the point in image number 2 gives me the epipolar line in image number 1. And obviously I can do exactly the other way around. I can compute the epipolar line in image number 2 only using the fundamental matrix and the point in image number 1. So this is the other important thing that we need to do. So we have the same for the other points. So I can express the line, epipolar line in image number 2 transposed gives times the epipolar, the point in image number 2 must be 0. And so the only thing that I now need to do, I need to have the transposition operator. So I know here that from this constraint, the epipolar constraint, I can then result that L double prime transposed must be x prime transposed equals f, so the other side of the equation, so that the result of this is, if I want to compute the epipolar line, it's just f transposed times x, so I need to transpose the fundamental matrix and take the corresponding point, so that I have the kind of symmetric part. I can compute the epipolar line in image number 2, given the fundamental matrix transposed, and the point computed in image number 1. So, and this is this reduction from the 2D space to the 1D space. So this is our prediction where the point must be in the other image. And just by searching along this line, I can look for the other corresponding point. And this is kind of the key thing which speeds up our search when we look for correspondences. So the image points must lie on our epipolar lines. And what we basically did so far, we just exploited this coplanarity constraint using the fundamental matrix, and then can derive symmetrically in the epipolar lines in image number 1 or in image number 2, just using the fundamental matrix and the image coordinate in the other image. And this was very easily derived through the constraint that the multiplication of a point in 2D and a line in 2D defined in homogeneous coordinates must be 0 if the point lies on that line. And this is the constraint that we actually have exploited here. So now we know how to easily get the epipolar lines just by exploiting the fundamental matrix. The next thing we want to look into the epipoles. So again, remember the epipole was the projection center of camera number 2 projected into image number 1 and the other way around. And this obviously is very easy to do. We just need our projection matrix and the projection center of the other camera. And this is something that I assume to know. If I know the matrix P, from the matrix P prime, I can extract this one, and from the matrix P double prime, I can express this projection center, and then I can directly compute the epipoles. So also computing the epipoles is something which is straightforward to do. And these are the points, as I said before, the epipoles here and there are the points through which all epipolar lines pass. And so that's kind of an important thing that we actually need to look into. So all epipolar lines pass through that epipole. That means for all lines L1, the epipole transpose times this line must be 0. And at the same time, for all epipolar lines in image number 2, the epipole of this image number 2 transposed with the epipolar lines which are generated must be 0. Okay, so this is an important property that we have. This means the epipole in an image multiplied with the fundamental matrix and a point in the other image must be always 0. So given through this equation, so the constraint that we derived, that all epipolar lines multiplied with the epipole gives me 0, this means that the epipole here will bring this expression always to 0. Right? So independently on where the other point coordinate is, because we know that all epipolar lines pass through the epipole. So at the epipole, it brings everything in here to 0. So with this equation, this means nothing else that the epipole is of the first image is the null space of my fundamental matrix transposed over here. So the null space of the fundamental matrix transposed is the epipole in the first image, and the null space of the fundamental matrix is the epipole in the second image. And this tells me something about the eigenvectors that I have of F. So the epipoles are the left and the right eigenvectors of the fundamental matrix and span up the null space of that fundamental matrix. So they are eigenvectors of F, and they are those eigenvectors that corresponds to the eigenvalues of 0. And so these are important properties that I can exploit when making considerations about where points have to lie, what is a null space of this fundamental matrix, and do certain investigations about these matrices and the whole geometry involved. And this actually brings me to the end of my very brief and rather informal introduction about epipolar geometry. So what we used with this epipolar geometry, we used an image pair and tried to derive what can we say about the geometry just by knowing that these are straight line preserving cameras. It means uncalibrated cameras. We discussed kind of epipolar geometry and what the key properties are there, such as the epipole, epipolar lines, epipolar axis, and epipoles. And the key thing why this is important is that it allows me to look for corresponding point in the other image. So if I know the relative orientation, so for example, the fundamental matrix, and I know an image in camera number 1, I just have to look along one single line in camera number 2 to find the corresponding point on that line. I don't need to search the whole image. And this substantially reduces the workload that I need to do, as well as the likelihood of making data association mistakes. And therefore, epipolar geometry will always pop up when you look for correspondences, or if you want to constrain certain things in an image, what must lie in which part of the image, about which points you can make certain expressions, like about the epipoles which form the null space. These are all things where epipolar geometry plays an important role. Thank you very much for your attention.